Here we're going to take a look at changing our trigonometric definitions. Up to this point, we've looked at the right triangle definitions of trigonometry, sometimes called the SOHCAHTOA definitions. But those limit us to any angles between 0 degrees and 90 degrees. And as we've already spoken, that we can have positive angles, negative angles, angles larger than 90, angles larger than 180, angles larger than 360, and all the same for radians. So that requires a change in the definitions, and that's what we'll take care of here. Like I said, they allow us to make use of trig functions for non-acute angles. And sometimes we call these the circular definitions. That way we can designate them from the right triangle definitions as being slightly different. What we start with is a coordinate plane with a circle centered at the origin and some initial ray in some position. If I then draw some angle and some, let's call it some first quadrant angle, that we call theta, and we want to find the trig definitions here. Now this, from here, if I want to find that, I can draw a right triangle by dropping a vertical from the point of intersection with the circle through there. And I can use my regular right triangle trig definitions that the vertical side is the side that is opposite theta, that the horizontal side is the side that is adjacent to theta, and the side that is part of the terminal ray, which makes the hypotenuse of the triangle. And that's all well and good, but that does not progress us anywhere in terms of our definitions. So what we'll do here is we will take and we'll say, well, you know what? The terminal ray intersects this circle at a point x, comma, y. Furthermore, the hypotenuse has the same length as the radius of the circle r. So from the center of the circle to this point of intersection, while it is the hypotenuse of the triangle, it is also the radius of the circle. Using the x and y, we can say that the adjacent side, the horizontal side, maybe I should use a different color here, the horizontal side right here is going to have a length of x. And the vertical side is going to have a length of y. So I can use my SOHCAHTOA definitions using opposite, adjacent, and hypotenuse and replace them with x, y, and r. And if I do that on my trig functions, sine of theta, which was under our right triangle definitions, the opposite side of theta over the hypotenuse, becomes the opposite side is now y, and the hypotenuse we now call r. Applying the same for cosine. Cosine of theta used to be under our right triangle definitions adjacent over hypotenuse. Adjacent has now been replaced with x, and the hypotenuse once again replaced with r. After that, tangent of theta. Tangent of theta under our right triangle trig definitions was opposite over adjacent. Opposite has been replaced by y, and adjacent by x. So we have our, maybe I'll slide that out of the way a little bit, make that a little more readable. Now we have our circular definitions. And then the reciprocal functions would be similar, that cosecant being the reciprocal of sine would be y, r over y. Secant, the reciprocal of cosine, would be r over x. And cotangent, the reciprocal of tangent, would be x over y. So those are the circular definitions of the trig functions and why they are named the way they are. Not just like, hey, here they are, take it at faith, but it's why the way they are. All right. Just as an FYI, very often when we're dealing with this particular situation, when we have our initial ray and our terminal ray somewhere, and we need a circle, very often we choose what we call the unit circle. The unit circle is a circle centered at the origin with a radius of 1. So recall from previous work that the equation of a circle, x minus h squared plus y minus k squared equals r squared. In this particular case, we're centering at the origin, so it becomes x squared plus y squared, and we are choosing a radius of 1. And it's just really nice to use because whenever I use my circular definitions now and I have to deal with r's in the denominators, the r of the circle, the radius of the circle, is 1, and I don't end up with any fractions. I end up with integers and nice neat numbers and so on and so forth. Don't forget, however, though, we would be using this particular point, x comma y. In this particular case, we have to say for this second quadrant angle, my x coordinate is going to be negative. So when I evaluate any trig functions that involve x, we're going to have to deal with that case being negative. So let's address some of those sign issues quickly right now, and then we'll move on to some examples in a second video. So what I'm going to do here is I'm going to draw the coordinate plane. And what we're going to do is look at these a quadrant at a time and look at the value, the signs of the trig values in any particular quadrant. Here I would say sine of theta is going to be positive. If we have a first quadrant angle, if my terminal ray lies in that first quadrant somewhere, that we are going to have sine of theta being positive. The reason is, if I have my initial ray and a terminal ray with some point x comma y and some radius r, well, we define sine of theta, I'll write it here, sine of theta to be y over r. In the first quadrant, the y is positive value. The r is always going to be a positive value. So a positive value divided by a positive value is positive. Thusly, sine of theta in the first quadrant, when theta is a first quadrant angle, is always going to be positive. So let me get rid of that. Just clean up a little bit of work here. Now, similarly, I can say that cosine of theta is going to be positive and tangent of theta is going to be positive. If you have your terminal ray in the first quadrant and you choose any point on that terminal ray, the x-coordinate is going to be positive, the y-coordinate is going to be positive, the circle is always going to have a positive radius. So no matter what ratio I take, y over r, y over x, it doesn't matter. Those outputs are always going to be a positive divided by a positive, which gives us a positive output. Okay. Let's move on to second quadrant angles. So if I have a second quadrant angle and I have some point x comma y there, and I'm going to have the circle is going to have some radius from the center to that point. If I take a look at the trig values for the second quadrant angle, I would say that sine of theta is going to be positive as well. Let me erase that. Greater than 0. Reason being, sine of theta defined as y over r. My y coordinate is positive, my r is positive, and if I divide two positives, I get a positive. However, cosine of theta is going to be negative. Cosine, defined as x divided by r, now in the second quadrant, this x coordinate is going to be negative, this r is going to be positive, and a negative divided by a positive is negative. So cosine of theta, when theta produces a terminal ray in the second quadrant, is going to be negative. And lastly, in the second quadrant, tangent of theta is going to be negative as well. Tangent of theta, defined as y over x, so I need the y, and I need the x. So let me grab on it. I need the value of x there. My y value is positive. My x value is negative. I divide them. I'm going to get a negative output. I would challenge you at this point to stop the video and do the same thing for quadrants 3 and 4. Use the definitions, look at the x-coordinate value being positive or negative, the y-coordinate value being positive or negative. I'll tell you that the radius is always going to be positive. I would challenge you to fill in quadrants 3 and 4 before you replay this, and I'll put up the answers for you. So why don't you pause it now, take those things, and start back in a moment. All right, maybe we're back. The values that we are going to need, I'm just going to put them up there, that in the third quadrant, sine of theta is going to be negative, cosine of theta is going to be negative, and tangent of theta is going to be positive. And in the fourth quadrant, sine of theta is going to be negative, cosine of theta is going to be positive, and tangent of theta is going to be negative. All right, so that's the introduction for the information. I'll make another video that has some examples about how we would use this. All right, thank you for listening.